Good afternoon, and thank you for joining us for the investiture of Dr. Ron Yu as the holder of the Tillis Weidenthal Professorship in Parkinson's disease and movement disorders research. I extend a warm welcome to all of you who can join us this afternoon, and especially to Dr. Yu's wife, Lim Ma, who joined us, as well as the extensive members and friends of the Weidenthal family who are with us today. It's a proud moment for all of us. It's a special opportunity for the dean to be able to recognize our extraordinary faculty, and to do so through recognizing the support that they receive from endowed professorships. I think the donor and donor families who contribute to our endowed professorships can't possibly imagine the incredible impact that such have on retaining our best scientists and recognizing their accomplishments and their future accomplishments and the commitments that our professorships and our professors make to our medical school. They really do recognize our dedicated faculty, their commitment lifelong to innovative discoveries, ultimately leading to therapeutics, better understanding of disease, how important they are to teach our next generation of researchers as well as practicing physicians, and really keep us at the cutting edge. And here in the School of Medicine, they each contribute to our mission, which I like to repeat, which is to improve health globally by linking research and innovation to patients and populations in a world-class environment for medicine and education, which is certainly what we have here in the city of Cleveland. There are remarkably 126 endowed professorships in the School of Medicine. Each of them brings to us an incredible amount of wealth and aura about who we are and what we do, and we couldn't possibly do it without donors and friends and families that keep those going for us. Now, the concept of professorship is pretty ancient, going back to 1540, King Henry VIII, who founded the Regius Professorship of Civil Law at Oxford University. There are now 6 Regius professors. And one, Sir John Bell, actually has a connection directly with Cleveland because he helped consummate the initiation of the Harrington Discovery Institute partnership with Oxford for rare diseases. So the lineage that we're discussing today goes way back, and for Cleveland and for Case Western, for the School of Medicine, the oldest professorships are the Hanna and the Payne families, who established professorships between 1901 and 1906. They are now held by Doctors Ann Harris in genetics, Agatha Exner in radiology and biomedical engineering, and the Hanna Payne Professorship, which is currently open, which was held by the late Nate Berger, and to find a proper candidate for that will take me a little bit of time, but I'm going to work on it. The professorship we celebrate today is made possible by Dr. Dan Tillis Weidenthal. If I can comment about him and then have him make a few comments. 1958 graduate of the School of Medicine and a professor to this day of ophthalmology. One of the longest serving members of our alumni board, and has been helpful to a number of our deans and my predecessors. Dr. Weidenthal's roots at Case Western Reserve are deep. His father, Clarence Milton Weidenthal, received his BA from Adelbert College in 1918 and received his MD from Western Reserve Medical School in 1921. His mother, Anna Tillis Weidenthal, received her BA from the Floristone Mather College in 1919 and graduated from the law school in 1922. His sons carried on the tradition. Jeff graduated from the law school and is here in 1988. David's in our dental school in 1989, is currently on our faculty. So I mentioned the Hanna family, and come to think of it, the Weidenthal family is getting pretty close. So thank you for your extensive and long-term support, and I'm looking forward to a continued relationship. Now, Dan himself did his undergraduate degree at Dartmouth. I understand has a grandson who's up in that neck of the woods at Bates. He then was admitted to the medical school by Jack Coy, who was the associate dean at that time and a single individual in charge of admission to medical school. You really couldn't get into medical school here without Jack. Many people call him Cactus Jack. I'm not sure if be careful what you sat on, but whatever. He then went on to do his ophthalmology residency, Dan, that is, at the Kresge Eye Institute in Detroit. Developed an interest and expertise in retinal surgery and disease. And then following his residency was at the Armed Forces Institute of Pathology on the Walter Reed Hospital campus during really the heyday. And for those of you who don't know too much about the AFIP, it was the premier secondary referral for almost any pathology in the United States during that period of time. Dan continued his ophthalmologic education at Mass Eye and Ear and the Retinal Research Institute. And then in '65, he returned to Cleveland and held the position of director of the residency program at St. Luke's Hospital in ophthalmology. And then moved on to a private practice at Science Park Drive in Beechwood in the late '90s and continued his practice there. And my hunch is he probably shared that office building with my spouse, who was an OB at Park Drive for many years. Dan's wife, Judy, was a noted large format photographer who graduated from Cornell in 1957 with a degree in art and architecture, and then came back to Cleveland. And Dan and she raised their incredible children and family, but I think it's fair to say, from what I understand, that Judy held the fort for the family because Dan was working long hours during those periods of time. Had to cancel appointments, I'm told, for emergency surgery, truncated vacations, and when they got away, Dan spent his time at meetings, and Judy got to enjoy the environment. She was incredibly well known, and her art and photography have been shown at the Gates Mills, at the Fairmount Center, and at the Jewish Community Center. Unfortunately, Parkinson's disease became her nemesis, and she suffered through it for more than 20 years prior to her death in 2017. The tremor became a real challenge, and she was no longer able to keep her practice in art going. But that led to Dan's initiation of the Thiels Weidenthal Professorship, and really helped him support our basic research programs here in Parkinson's disease and in neurologic science. I should point out that Dan and his family also established a second endowed professorship after long discussions with my predecessor, Pam Davis. The Weidenthal Family Professorship in Career Development supports an early career faculty member working in academic areas of greatest impact in the future of medicine, and that is currently held, and I see Paula in the back, by Dr. Paula Filipendo, whose lab is foremost in the area of genetics and neuroscience and understanding pathways, and very active and much appreciated by the school in her directorship of the Neurosciences PhD program. I mentioned that Dan, as a ardent alumnus of ours, is a very strong supporter, in addition of his alumni class scholarship fund rather, and he's been incredibly active helping others to support our medical students. So at this time, I think I'm going to let Dan, if we get him a microphone, correct things I've said. Dan.
Stan, I want you to remember the 127th professorship is going to be one of the most important during your tenure. I'm going to see to that, because we are adopting Ryan Yu and his family. So we're going to take care of them, and you know, you take care of the rest of it, but we'll do it. And I got to tell you that when it came down, it was my mother was Ann Tillis Weidenthal, and so now when that comes up, there must have been was there a singer or something? So who the heck was Mel Tillis? But they want to know if we're related. So I had to look it up. So I said yes. So, you know, then they said, well, we'll do it in G this time. I said, I'm not doing it. So anyway, the thing that I want to do is to be sure that Ron and his family are integrated into the community and are happy here. Because when you're happy at your work, you know the rest of it takes care of itself. And so we hope it will, and our family, David Weidenthal and Jeffrey Weidenthal and their families we're adopting the Yu family. So I'm not, I can learn a little Chinese, you know, but we'll do it, okay? So Stan, you do it. We're gonna make the 127th, because the brain neurologic disease is what's smiting us, and our progress has been painful. So we need the best and the brightest, and I'm so pleased, Stanley, that Stanford, that you did this, because this is, I think, one of the most important professorships in the medical school. That's what I have to say.
We've taken some pictures with you, and I have a very, very small, light gift for you, which is a school medicine photo frame, and we'll fill it with the pictures. I'm going to turn this over. So Dan, thank you for your warm and thoughtful remarks, and as we've come to learn, your both strong advocacy and incredible commitment to the future. And I do happen to agree with you that neuroscience is the most important next frontier. That's coming from a cancer doc, but I appreciate that this area needs our urgent attention. So let me tell you a little bit about Dr. Yu. Prior to joining us as the chair after a national search in the Department of Neurosciences, Dr. Yu served as a senior investigator at the Stowers Institute for Medical Research in Kansas City and was a professor of neurosciences at the University of Kansas Medical Center. Here at the school, proudly, the Department of Neuroscience is known as a state-of-the-art, really quite highly regarded basic science department into the biology and pathophysiology of the brain, neurotransmission systems, neural circuitries, stem cell plasticity, the role of genes in circuit formation, in development, and in disease. Dr. Yu's goal is to maintain and expand that expertise. He keeps reminding me of the expansion part, so thank you. And to increase the visibility of the department across the entire city through training and collaborative efforts. The department itself really does have an exceptional track record of training graduates, postdocs, undergraduate students, and we're hoping to expand the research support with our MD colleagues. When Ron joined, and to Dan's point, I talked about our Brain Health Collective, which we've been brewing for now close to a decade to try to bring all the individuals across Cleveland together. And if you do the calculation, there's as much research going on in the city of Cleveland in neurosciences as there is in cancer, so it is ripe time for us to gain that support and recognition and to coordinate it through, I think, Ron's leadership and through the Department of Neuroscience, and that's really putting a stake in the ground, as Dr. Weidenthal said, to really create important areas of activity. Now, in terms of Dr. Yu's own research, he studies the neural circuitry of behavior by studying the olfactory system. For those of you who aren't in the field, that means how we smell. It took me a while to realize that. But it is, in fact, if you think about it, we get exposed to that sensory all the time, every day, and it's the area that requires the most turnover and modification throughout life. In fact, it's an incredibly important area for neural stem cells and for linkage to our learning areas, and we now know is critical in disease. Many of us lost our smell during COVID, and those of us suffering from a neurologic degeneration condition will also lose our smell as well. So understanding the biology of that and coming up with diagnostics and therapeutics is critical. Dr. Yu has been exceptionally well funded. He's currently supported by 3 NIH R01s, which haven't hit the administration sensitivity index. He combines molecular genetics, electrophysiology, optical imaging, and animal behavior studies in his work. Now, since coming to Cleveland, I'll note that when Ron arrived, I said, I want you to go out and visit your colleagues across neurology, neurosciences, the hospitals, get to know people across the city of Cleveland. Now, he never tells me his itinerary, but each time he goes and gives a lecture, I get 5 or 6 emails, all positive, thanking me for bringing Dr. Yu to Cleveland. So he has already made an impact on his own development, and I appreciate his time and effort doing so. I'll also comment that when he was doing his postdoc with Richard Axel, and I'm sure he'll tell us a little bit about that, a Nobel Prize-winning neuroscientist at Columbia University, he made enough of an impact and impression on Dr. Axel when I called for a recommendation. It was hard to get off the phone with the accolades that I heard. So, Ron, you come incredibly well recommended, and we'd love to have you come up and give us a few words.
Well, I'm incredibly honored to be here, and thank you, Dan, and the Weidenthal family for providing this chair to me. I was supposed to tell a little bit of myself, I guess. And I'm not sure if I'm going to please you, because in my early history, I was never interested in biology nor medicine. So this is my humble beginning. This is a picture that I can find because I'm moving. Of the first year when we were in middle school. And And that time, we really didn't have much. With no cell phone, not even a telephone in the house, no television. I did not hear about those things. And sometimes we literally don't have enough to eat. But we were happy because we can play in the field, play with mud and making your own toys. And my favorite activity is this, stargazing. So at that time, there's no light pollution. And so you can really see all the constellations, all the stars in the night. And I was really intrigued by the universe. And I really wanted to be an astronaut and astrophysicist. So I made my own telescopes, looking at all the moon, trying to look at to document the solar and lunar eclipse. And I even wrote a novel about landing on the planet in Alpha Centaurium. So I don't know if there's one yet to be discovered. But that's what I wanted to do. I really wanted to be an astrophysicist. And in fact, when I was trying to apply for college, that's the first thing I wanted to put into my selection. But fate intervened. So these two men, so they kind of changed my fate, my fate. These two are the chair and vice chair of the Department of Biological Science and Technology of Tsinghua University. That's my alma mater. And that university was established in 1911 with the Boxer indemnity from the U.S. government, because that's the money that the Qing dynasty paid for the Boxer Rebellion, which killed many missionaries, including the ones, I think, from Oberlin College, just learned from Jeff today. But this is known for engineering school, right? And these two men basically decided that they're going to establish a biological science department in that school. And Mu Ming promised all of our new recruits, we were the first recruit of undergrads in that school, that all of us are going to go to the US. And facing a grueling 3 days of tests for college entrance exam, which I will be exempt if I go to this college, I decided, yeah, that's a good idea. So I choose to go to Tsinghua University, and it turned out that we had nothing. We have to borrow professors from Peking University, but we have a lot of good engineers and physicists, which is fine by me because I wanted to study physics, not biology. But Mu Ming really introduced the idea of how do you study for yourself rather than, in China it used to be just raw memory-based studies that you have to memorize a lot of different things. And this is one of the earliest things that in our first year in college, Mu Ming was holding those seminar series. So we can discuss papers, and that's just a real eye-opener. And I really got introduced to how to study biology. And that's me in that corner. But I was just happy to gain, my degrees in both physics and biology. And then I went to Columbia University and joined the lab of Lorna Rowe. She's now at the NDS. She was the director for a few years during COVID period. And during that period, I was using my physics to study ion channels. And that's my first introduction of the biology. How do you use physics to study biology? And I built from scratch the rigs that I've used, and now I was a happy camper once I get into that room, close the door, start recording. Because I can see how electricity passes through cell membrane, and you can really do single molecule biology there because you're recording single channels. That's one molecule at a time, right? So at that time, I was studying the nicotinic receptor system. And that's part of the cholinergic system that the brain uses and peripheral nervous system also use, that projects to all parts of the nervous system. And at the end, where this happens is that presynaptic cells releases a neurotransmitter acetylcholine that can activate the postsynaptic ion channels. And I was particularly interested in how the composition of these ion channels can change the way that neurons respond. So it turned out that I was studying one of the subunits called alpha 7, and the other one's alpha 5 that combined with alpha 3 and beta 4. Alpha 7 turned out to be a very important subunit in brain and in peripheral, and I think some of the treatment for Parkinson and the Alzheimer's disease relying on cholinergic input are hitting those receptors. But my true appreciation of biology did not come until I met this man, Richard Axel. I joined his lab without him knowing, without myself realizing it. I was just temporarily holding there, and then 8 years passed. So this is Richard after he's won a Nobel Prize. The Columbia University run this cover. And this is him, always wear a suit, but never irons his shirt. And they put him on cover. And he never touched a rig before, and now he's posing in front of one, trying to show how he can do a 2-photon imaging experiment. So I was really attracted by his intellect, and I'll tell you how. And what I meant by that, he kind of exposed me to the idea of biology. So I was interested in physics because physics provides simple answers to the universe. Right? So you look at quantum mechanics, you look at theory of relativity, that kind of explains a lot of things with a single equation, with simplicity. But biology is the opposite. Basically, you can have the same principle, but you have this massive, infinite diversity you can generate in the forms of biological entities and how they function, right? So this is what I really found that in his lab, being the only neurophysiologist for many years, and in the sea of molecular biologists. So there we studied the olfactory system, as Stan mentioned. So just a very brief introduction. We studied the mouse. This is a picture of the mouse head. And if you peel back and look inside, you can see the brain and then the nasal cavity, where air comes in and interacts with the olfactory epithelium. So in this olfactory epithelium, Richard's work together with Linda Buck, that won their Nobel Prize, is to identify this large family of receptors that detects odorant. And these odorant receptors are expressed by the olfactory sensory neurons. Each neuron expresses only one receptor. Right? So that's a unique genetic problem, because how do you select one out of the 1,000 receptors to be expressed? That's a genetic problem. But we're interested in neurobiology. So you can see how this receptor information detecting the odorant presence being transmitted into the brain. What they found that together with Peter Mombart and other members in the lab, they found that each neuron expressed the same receptor, and the thousands of neurons expressing the same receptor, when they converge, when they're projecting the axons into the brain, they converge into a single spot. And with 1,000 different receptors, you have about 2,000 spots, because the other side have another 1,000, that you have this stereotypic map of the receptors. So now if you imagine your homunculus, you look at the map, the idea is that you see different combination of receptors being activated, you know which odor it is. Okay? That's a simple idea. And we're going to be able to show that. And downstream of these glomeruli are these microtufted cells, which also show this one-to-one relationship to this. So one of the problems we're trying to understand is how does a neuron, out of this sea of randomly distributed sites, is able to find this direct connection. So how do we do this? The way that a biologist goes through about this problem is that we find a way to perturb it. If we can perturb it, we know there is something in there that probably drives this process, right? But the problem is that for many years, they can't find a single way to perturb this. And one day, I was walking down the corridor, and Richard was talking about the experiment they did. He said, we deleted the mitral cells. We deleted the other cells, and the map still forms, and there's no perturbation. We deleted many different genes, nothing happened. So I was like, how do you delete a cell, right? And he said, nah, it's the molecular shenanigans. I said, no, what exactly is it? He said, transcription factors. So that's when a light bulb light up in my head. I said, I want to do this, because I want to do things like this. I want to delete cells, I want to delete things, I want to change the way things. So at the time, we were trying to find a way to perturb this map, right? And so I said, okay, so neuroactivity is important. Maybe neuroactivity is important in this process. He said, but it's hard to do, because in most of the classic experiment, you block neuroactivity by providing toxins, putting toxins in the developing brain. But as many of you know, that you on your spare time, you're trying to inject toxins into a pregnant mouse during the embryonic development, it's really hard. And this thing don't stay, and you probably kill the embryo anyway. So we're trying to find a way to perturb this system. And it turned out that I know a little bit about ion channels, because that's what I studied. So most ion channels, when it's basically conducting ions through the membrane, when you have positive ions coming into the membrane, you excite the cell. And when you have positive ions flowing out of the cell, you depress it. And basically, that's the basis of excitability of neurons. So I decided that, okay, so if you have a leakage potassium channel, allow a constant of efflux, outflow of potassium channels, you can suppress that neuroactivity, right? So that's the idea was born. And so what I decided to do is to express one of the potassium channels, and then in a genetic way, so that we can silence only the olfactory sensory neurons. That idea was born, and I told Richard, I said, I want to make a mouse to do this. And he said, but you're my electrophysiologist. But I said, I want to do this. He said, okay, go ahead. 9 months later, my mouse was born, and we can silence the neurons. So without silencing, this is just labeling the same thing, that you can see the axon converging. And but if you silence neurons, you cause a massive perturbation of this projection pattern, right? So that's what we found, and the published that paper, got a job at Stowers. And 10 years later, Li Mei, who was with me at the time, and we did this experiment, and then we found that this perturbation actually is time dependent. It only happens if you silence neurons during the first week of the postnatal development. And we define that as a critical period. So silenced neurons can do this, but in fact, we found out later is that if you overexcite the neurons, you also perturb this projection pattern. So for example, if you have two neurons to projecting the two glomeruli, and if you expose the animal to an odor that activates those two receptors, you end up with multiple glomeruli. So this is just imaging showing that if you expose odor to this animal, then the receptor neurons detecting those odors becomes numerous in their final. And that happens during the first week after birth. So as I mentioned to you, when you have these pattern changes, you change the way that the animal perceives identity. But how do we demonstrate that? So this is actually one of the first experiments we did in the lab when I set up at the Stowers. Li Mei made the mouse to express that genetically encoded calcium sensor that can read neuroactivity. And we can express that only in the olfactory sensory neurons and look at in the glomeruli what happens when you deliver odorant. So this is a movie showing that when you deliver odorant, you see the flashes. Every time you see a flash, that's a different odorant. And they have different patterns. So we can see that, say, for example, banana smell activate a few of these glomeruli. this old shoe smell, activate the much broader ones. And hexanoic acid actually is really stinky, activate the very frontier of it. And that movie was the very first movie we got from the first mouse we had. So it was a very exciting moment. So that we can read the mind, we can read the neural activity, read the brain activity from these mice. But how do we tell whether the animal actually smells differently, right? So we have been developing behavior paradigms to read off. So here is one example. As I mentioned, that when you expose the odors to the animals, you change their axon projection patterns. So what happens to the animals? So we can expose the animal and take the odor away and then test them in adult. So this particular experiment, we are using this called threat-induced escape choice experiment. So we are relying on the animal's innate a tendency to avoid being the prey. So when there's a looming signal coming from above, the animal trying to escape, right? But where they escape to, depending on what they're smelling. So we can do this by giving 2 igloos that the animal can hide. And we put different odorants into different igloos. And now we trigger this alarm to the animal. So this is a movie showing this mouse that's moving around, sniffing around. Those 2 igloos have odorant. And when it's in the middle of this position, we provide the looming signal, and the mouse dart away to those one of the odorant, right? So it turned out one of the odorant that if we put 2 odors, one is acetophenone, it's aversive to the mouse. The other one is eugenol, it's neutral to the animal. They will avoid the aversive one, choose the neutral one. However, if you expose this animal to acetophenone during the first week after birth, and now they grow into like acetophenone, and that signals safety for the animal. So now they choose acetophenone. So basically, we can turn this innate attraction or avoidance, this odorant, and then by exposing the animal to, say, an odor that usually drives them away, and turn that into something that is for their nest recognition. So that has this big impact. Experience basically can change the valence of the value of that signal to the animal. So that's currently where we have been doing, and we have been working on a number of different projects. And before I going on to tell you what we're going to do next, and this is time of reflection, because I think we, as a scientist, have been living in a privileged life. It's because we don't, especially basic science, we don't make any money. We don't make any product. We make discoveries. But being able to do that is really a privilege to do that. And I was in Florence earlier in the summer, and I went to admire the sculpture of David. And Michelangelo was supported by the Medici family, right? So it's the Medici family that enabled all his creativity to come to fruition. And that's, the public support of science, actually in the US at least, did not come about until the 50s. During the Sputnik, I think that's when we are trying to compete with the Soviet Union. But just the last few months of experience also tell us that this can go away as well. But we have benefactors, like the Weidenthal family, that continue to support science, and that will enable us to go on, I think, for the indefinite future. And I thank you for that, and I think we will continue to do that. So for the future, in my lab, and also we will be going into to build up this brain health initiative. So, for example, we can identify the molecular mechanism of plasticity and the resilience, and what determines the regeneration of olfactory neurons, because that's one place regenerates throughout the life of the animal. And we can identify mechanisms like neurodegenerative disease using this basic model to look at how that causes the neurons to die to dysfunction, including Alzheimer's, Parkinson's, and long COVID. We have collaborations with virologists. It turned out that long COVID is induced by neuroinflammation that can cause selective death of dopaminergic neurons. And we can also find target for nerve damage repair. And okay, I'm going to skip the next one. And I want to thank, it's getting very slow, sorry. The lab, who has contributed to many of this work. So I mentioned Limi and 6 of the members, Thelma, I, Rahul, Devin, and Ian, and Lynn all came with me from Kansas City to join me here. And also, we have joined by Yihui and Bruce from Jerry Silver's lab. So we'll continue work with Jerry's work on spinal cord injury. And I also want to thank the department. This is our Memorial Symposium picture from Lynn Landmaster and Jerry Silver's Memorial Symposium. And I want to thank the department to give me this really big welcome, making me really feel at home since the first day I arrived. And I also thank Stan and the chairs who has been helping me get oriented. Again, I want to thank Dan and your family to continue to support this endeavor. And thank you all for your attention.
Thank you, Ron, for a wonderful presentation. And now I get to ask you to sit in the Tillis Weidenthal Professorship chair. Congratulations. I certainly enjoyed your remarks, and I learned something. I'm sure everyone in the room did. We have a reception outside. We did all our pictures early, so please join us. And thank you all for coming.
Good. Cheers.